All right, so for this topic, we're going to be talking about the first and second derivative tests and what they can tell you about the graph, or rather the behavior of the graph of your function. So, first of all, here's what the first derivative test says. If I have a function f of x, whatever that is, and I take its derivative, f prime, wherever the derivative is less than 0, I know that the slope of my original function is negative. So wherever the derivative is negative, I know that the function f of x is decreasing. If f prime of x is greater than 0, then f of x is increasing, positive slope. And wherever f of x equals 0, my function is constant, which could mean that we change direction. So let's go ahead and take a look at that right quick. So if I've got my graph here, and let's just say it's an arbitrary function, I'm going to try to make it as wiggly as possible. Something like this. Okay? So again, barring horrible art skills, if we look at this, a place where the derivative would be less than 0 would be like right here. Why? Because the slope is negative. It's going down. So f prime is less than 0 at places like that where the slope is 0. And you can see, or the slope is negative, apologies, less than 0. So you can see that wherever that happens, you have a negative slope. And so if you were thinking of walking left to right, like if these were little hills, you'd be going downhill wherever the derivative is less than 0. Likewise, wherever the derivative is greater than 0, so like right here, you're going uphill. This is where f prime must be greater than 0. And if you get to the top of the hill, at least at that moment, you're neither going uphill nor downhill. There's a certain point at which you'd reach a peak, and you wouldn't be increasing or decreasing. Now, it's possible that you could change, right? So you could be going uphill, hit 0, and start going downhill. It's also possible that you could stay the same. And so we see something like that. Let's say I modify the back of this graph a little bit, like back here. So it looks like this, which is something like what x cubed does. Right at this point, you were increasing, you had a positive derivative, then it was 0 right here, but then you still keep increasing afterwards. So at points where the derivative equals 0, you could change direction if you keep going, or you could just keep increasing after you stop for a moment. Or of course, it could just stay flat for a while as well. All kinds of things that could mean. Also keep in mind, it's not necessarily a peak, because right over here, f prime is equal to 0 as well. And so that's a minimum value. So the first derivative test, wherever you set it equal to 0, you're very likely to find either a local minimum, a low value, right? So if I move either left or right, I'm forced to go uphill. Or you find a maximum value. If I move either left or right, I'm forced to go downhill. But that's not always true, because right here at x cubed, you've got this point here, but if I move left, I go downhill. If I move right, I go uphill. And this is neither a minimum or a maximum. So simply looking at where it's equal to 0 doesn't tell you whether you have a minimum or a maximum or neither. But what you can do is you can look on both sides of this point. Notice over here, f prime is greater than 0. It's a positive slope. And to the right of this point, f prime is greater than 0. So I know if I look to my left and to my right, then I know this isn't a minimum or a maximum. Likewise, if I look over here, if I look a little to my left, I'd have to go uphill. If I look a little to my right, I'd have to go uphill. I know I'm at a minimum. And likewise, if I look here and I look at f prime is greater than 0 over here and less than 0 over here, now I know I'm at a maximum. So you can do that. But that involves a lot of calculations, right? You've got to keep looking at f prime for different values to the left and right. So there's something else you can do. You can take the second derivative, f double prime. So this is interesting. If this is less than 0, then what you have is called concave down. And it looks like that. At some point on the curve, you've got a downward cupping going on. Well, that's useful because, for example, if I look up here at this point, f double prime, around this area anyway, that's concave down because it's less than 0. Well, if I'm concave down and f single prime was 0, I know I'm at a max. That's a lot easier. Likewise, if f double prime was greater than 0, I'd have concave up, which looks like this. So for here, f double prime is greater than 0. So here, if I know f prime is 0 and I know f double prime is greater than 0, then I know that I'm at a minimum right there. What about this place over here where it was neither a max nor a min? Well, that's where f double prime is also going to equal 0. And we call those inflection points. And so that's places like right here. So if I look here, I know f single prime is 0 and f double prime is 0. Then I'm at an inflection point. So the first derivative test lets you tell where you're increasing or decreasing. And when you put that together with the second derivative test, which tells you whether you're concave up or concave down, you can use these together to easily find your minimums, your maximums, and your inflection points. And so that is an overview of the first and second derivative tests and why they're useful for your graphs of a function.